For decades, scientists warned that bees can't survive without flowers. But in Texas, officials gambled anyway, releasing 10,000 bee packages across barren farmland. Within 48 hours, 85% were dead, and the site was shut down. Yet, as officials scrambled to contain the disaster, a few colonies refused to die. What investigators uncovered in those survivors could turn the future of agriculture on its head. But why were the bees sent here in the first place? And what did it cost to find the answer? Trucks pulled up just after sunrise, each loaded with wooden crates stacked 3 high. Shipping manifests listed 10,000 bee packages, each one a mesh-sided box pulsing with life, each holding around 10,000 honeybees. Workers moved quickly, unloading crate after crate onto the edge of the field. There were no wildflowers, no blooming crops, just dry soil stretching in every direction. The only sign of preparation, a few shallow furrows cut into the earth, where the bees were meant to be released. The first packages were opened at 8:13 a.m. on site field. Cameras recorded swarms rising in tight, frantic clouds, searching for color or scent in the dust. Bees spilled out, fanning across the ground and into the air, but within minutes, the confusion was obvious. Some circled, then dropped back to the dirt, wings beating in the heat. Others clustered on the empty crates, as if waiting for direction that never came. By midday, the temperature climbed above 90 degrees. Footage from motion-triggered cameras caught the first signs of trouble. Bees crawling in slow, aimless circles, then lying still. Workers stepped carefully between growing patches of motionless insects, checking thermometers and jotting notes on clipboards. The hum of activity faded as the afternoon dragged on. Night brought no relief. Without nectar or water, the colonies weakened. By the second morning, the ground was littered with bodies. Field teams counted losses by the hour. The mortality rate climbed past 50% by the end of the first day. By the 48th hour, over 85% of the bees were dead. The official tally: more than 8.5 million bees lost before a single flower had opened. The site was sealed off by midday on the second day. Officials taped off the field, collected samples, and shut down operations. Shipping logs and on-site camera footage became the only record of the event. The experiment, meant to test survival, had turned into a quantified catastrophe. The scale of loss was undeniable. Hard numbers written into every manifest, every frame of camera footage. But as the dust settled, a handful of hives showed faint signs of life, raising a new set of questions for investigators. Maria Torres stood at the edge of the field, hands still shaking from the night before. She had worked bees for 20 years, but nothing had prepared her for the sight that morning. Acres of ground carpeted in gold and black, the air heavy with the silence that follows disaster. Her voice, caught on a cell phone recording, carried the disbelief of someone who had watched hope vanish in a single season. Maria said they just stopped. All at once. I've never seen anything like it. By noon, a convoy of state vehicles rolled up. Yellow tape unfurled around the site, cutting off access to anyone without a badge or clipboard. Officials from the Texas Department of Agriculture moved with quiet urgency, logging coordinates and snapping photos of the scene. Drones buzzed overhead, sending back wide-angle shots that captured the scale of the die-off. In the footage, the field looked like a patchwork of sun and shadow, every dark spot a cluster of bee bodies. Cleanup crews, dressed in white coveralls, began the painstaking work of collecting samples. They moved methodically, scooping bees into sterile bags and labeling each with the hour and quadrant. Metal crates lined up along the tape, some holding live specimens that barely moved, others packed with the dead. The protocols were strict. No outside contact, no unsupervised entry. Every step was documented and every sample archived for later analysis. Dr. Luis Herrera, a forensic entomologist from Austin, arrived that afternoon. He crouched near the shallow furrows, examining the soil and jotting notes in a spiral-bound field log. His team set up a mobile lab at the truck tailgate, prepping slides and vials for transport to the state facility. Herrera spoke quietly with Maria, asking about the timeline, the weather, the behavior of the bees as they failed. His questions were precise and clinical, but his face betrayed the weight of the loss. The field was locked down for 3 days. No one outside the investigation team crossed the tape. Local reporters gathered at the road, trading rumors about what might have gone wrong. The official statement confirmed only the basics. The site was sealed, samples were being processed, and all operations were suspended until further notice. Shipping logs and drone footage were secured as evidence. For Maria and the other workers, the wait was endless. A forced pause as experts sifted through the aftermath, searching for the reasons behind a catastrophe that had unfolded in plain sight. In the years leading up to the experiment, the landscape across much of Texas agriculture had changed in ways that few outside the industry noticed. Fields that once burst with wildflowers in spring now stretched for miles as single-crop monocultures. Cotton, corn, sorghum, planted edge to edge, leaving little room for native blooms. Surveys taken in 2023 found fewer than 6 flowers per square meter on many commercial fields, a density too low to support even the smallest wild bee populations. For beekeepers and farmers alike, the numbers told a story of slow decline. Texas honey revenue, which had reached $27 million just a year earlier, crashed to $11.8 million as drought and heat waves left hives starving for nectar. Projections from the state's agricultural economists warned of a $43 million deficit if pollination rates continued to fall. Dr. Shalene Jha, an ecologist at the University of Texas, watched these trends with growing alarm. Her research showed that even small strips of wildflowers along a field's edge could boost cotton yields by nearly 20%, yet those margins were vanishing under pressure to maximize every acre. Dr. Renee Chang, an agricultural economist, described the mounting financial stress in plain terms. If you are losing 1/3 of your bees each year and your crops still need pollination, you are caught between a shrinking supply and rising costs. The economic squeeze reached all corners of the industry. Commercial beekeepers, once able to move hives from field to field following the bloom, found themselves hauling bees hundreds of miles just to find enough forage to keep colonies alive. Some operations lost over half their colonies before pollination season even began. Farmers faced with fewer bees and higher rental fees watched fruit set and seed yields decline. The math was relentless. A single lost hive could mean acres of underpollinated crops, with ripple effects up and down the supply chain. Pressure mounted for a solution, but options were limited. Federal subsidies for pollinator habitat lagged behind the scale of the problem, and most growers resisted setting aside land for flowers that did not pay by the pound. In meetings and conference calls, experts debated whether to invest in habitat restoration or to push for more resilient bee stocks. Dr. Jha argued that landscape diversity was the only proven way to stabilize yields, citing studies where even narrow ditches of untamed plants increased bee visitation by 18 to 20%. But in a year when honey prices crashed and insurance payouts barely covered losses, few growers were willing to take that gamble on wildflowers. The decision to attempt a high-risk field trial grew out of this economic and ecological deadlock. With revenue in freefall and pollination deficits looming, Administrators approved the release of thousands of bee packages onto land that, by every metric, was a forage desert. The hope was that a subset might survive, revealing traits or behaviors that could be scaled up to rescue a battered industry. But the underlying reality was stark. The experiment was less a bold leap forward than a last-ditch effort by a system strained to its breaking point. Lab results from the sealed-off site arrived at Texas A&M's entomology department just days after the cleanup. Dr. Garrett Slater, a honeybee specialist, reviewed the samples under bright halogen lamps. The first culprit was easy to spot: Varroa mites clinging to the legs and abdomens of dead bees by the hundreds. Slater's team ran resistance assays and found that more than 3/4 of the mites, 78%, survived amitraz treatment, the chemical most commercial beekeepers still rely on. This level of resistance, once rare, had become the new norm in Texas colonies, making routine mite control nearly impossible. In parallel, Dr. Malcolm Price, a toxicologist, analyzed pollen and wax residues from the few surviving hives. His chromatography results revealed a chemical cocktail: traces of neonicotinoids mingled with fungicides and herbicides, even though the field itself had not been directly sprayed. Price explained that bees foraged far and wide, picking up residues from distant fields, then bringing them home in pollen baskets. Alone, each chemical might have been survivable. Together, they acted in synergy, weakening the bees' immune systems and amplifying the effects of viruses and mites. The impact of these hidden killers rippled outward. As word spread about the die-off, commercial beekeepers across the state scrambled to secure replacement colonies. The sudden scarcity drove up the price of pollination contracts overnight. By the end of the month, rental fees for a single hive had jumped by 37%, an increase that caught both farmers and brokers off guard. Watermelon and melon growers, already facing thin margins, wondered if they could afford to plant at all. Some fruit set was left to chance, while others turned to out-of-state suppliers, only to find that losses were just as severe elsewhere. Agricultural economists tracked the fallout in real time. They noted that pollination shortages were no longer isolated incidents, but a structural risk for Texas food supply. As Dr. Price put it, "We are not just losing bees, we are losing the buffer that keeps our crops productive when the weather turns or the land fails." Behind the numbers, the survivor hives from the experiment stood out. They had somehow avoided the worst of the pathogens and chemical residues, raising urgent questions about what set them apart. Field teams flagged these colonies for deeper genetic and physiological testing, hoping to find clues that could help build a more resilient pollinator workforce. The search for answers would move from the devastated field to the lab, where the smallest differences might hold the key to future survival. Dr. Aisha Kumari reviewed the survivor colonies under a microscope, searching for any clue that separated these bees from the millions lost. Tissue samples revealed a pattern. The survivors showed a marked increase in HSP70, a heat shock protein known to protect cells from thermal and oxidative stress. Lab assays confirmed HSP70 upregulation, a response typically seen only in bees exposed to repeated environmental extremes. This molecular signature suggested the survivors had activated a genetic defense, buffering them against the relentless heat and starvation of the barren field. Further analysis turned to the bees' microbiome. DNA sequencing of gut bacteria uncovered a distinct profile with high levels of Snodgrassella, a core symbiont linked to immune resilience. In contrast, most control colonies, those that had perished, showed signs of microbial imbalance, with opportunistic bacteria crowding out beneficial strains. The survivors' stable microbiome hinted at a hidden advantage, allowing them to process scarce resources more efficiently and resist pathogens that swept through neighboring hives. Behavioral data added another layer. Field cameras set to record at dawn captured the survivors, leaving their hives before sunrise, foraging in the cool hours when competition and heat stress were lowest. This early activity pattern, rarely observed in managed colonies, matched what Dr. Kumari had seen in wild populations forced to adapt to unpredictable environments. Together, these traits, molecular defenses, microbiome stability, and altered foraging rhythms formed a profile of resilience that went beyond chance. For the first time, the data offered a concrete path to understanding how bees might persist in landscapes stripped of their usual lifelines. Greenhouse trials offered the first glimpse of what these survivor bees could mean for farming. When colonies with the same molecular and behavioral traits were introduced to controlled tomato plots, researchers tracked a 24% increase in fruit yield compared to standard hives. The difference was visible row by row. More blossoms set, more fruit matured, and fewer malformed tomatoes at harvest. These results caught the attention of Mark Delgado, a food security analyst who had spent years modeling the risks of pollination shortfalls across Texas agriculture. Delgado argued that the lesson was clear. Resilience in bees could translate directly into resilience in the food supply, but only if the landscape gave them a fighting chance. Delgado pushed for a new approach, one that went beyond emergency hive imports or chemical treatments. He called for a statewide incentive to set aside 5% of every commercial field as a pollinator buffer, planting strips of wildflowers and native grasses along the margins. His models predicted that even this small fraction could stabilize yields and reduce the need for costly hive rentals, especially in crops like tomatoes, melons, and cotton. Policy debates followed, with some growers skeptical about losing acreage, but the data from the greenhouse trials made the argument harder to ignore. For Delgado and a growing number of advocates, the path forward lay not in chasing the next chemical fix, but in rebuilding the margins, restoring the wild edges that once made Texas fields a haven for pollinators. Today, misinformation spreads faster than facts, especially when it comes to environmental crises. As pollinator populations continue to decline, real solutions depend on rigorous science, not viral myths. The absence of evidence in Texas reminds us that every claim shapes public policy and perception. Truth is fragile. In the fight for our food future, it is more essential than ever. What do you think? Join the conversation below.